Welcome back to my channel. Today we're going to be talking about another dynamic programming pattern, the unbounded knapsack. So, the unbounded knapsack. Now let's go back to the beginning. So what is a knapsack? So imagine that we have a knapsack, yeah, and then this knapsack happens to have a capacity. Capacity is like the the size of the element it can contain, and then we now have a couple of balls that have a weight. Yeah, so let's say that these balls with weight are represented using an integer array. One ball has a weight of 1, another ball has a weight of 50. And then these balls, they also come with a particular value. Yeah, so, and then the values are also represented as another integer array, such that the one with the weight of 1, has a value of 1, and then the one with the weight of 50 has a value of 30. Now the task now is to fill up this bag that has a capacity. So let's assume now that the capacity is 100. Fill up this bag that has this capacity of 100 such that the value of the content of this bag is maximum. Does that make sense? Yeah. So that's the unbounded knapsack problem. This is a knapsack, and then you need to fill it up with some elements whereby there are some sizes and values to these elements. So we know the 01 knapsack problem, which was pick or not pick. For this one, the unbounded knapsack problem, we have, for the 01 knapsack problem now, for example, when we had like an input array of elements, 3, 4, 0, 1, like that, let's say 6. At every point, we had a choice of pick or not pick, pick or not pick. And then once we do a pick or not pick, we immediately progress forward. We forget that input, we move on to the next index, remember. Yeah, but for this unbounded knapsack, the interesting thing is we have an unlimited, we have an unlimited number of balls that we could pick from. Like an unlimited number of selection. That means that we can select one, 100 times if you like. You can select 50, 500 times, as long as it fits into the capacity of this bag. So it's not as if we need to only select one once, and then once we select one, we've already used that ball. We now need to select another kind of ball. No, we have an unlimited number of each of the option. That is what makes it unbounded. Does that make sense? Yeah, so let's just quickly go into what to look at to solve this problem. So what we will basically do, from what we've been saying before, we will have, in this case, we'll have a DP here, and this is basically what we'll be doing is we'll be selecting different options. So it will look like something like this. We'll have a loop. Within that loop, we'll decide if we should pick one weight or we should pick the next weight. And if it happens that there are other weights too, we need to decide whether you need to pick weight of y or weight of x. When we pick each of these weights, we'll have a value that will store the amount of values that we've accumulated so far. And then the moment you pick up a weight, we immediately say, so for example, if there is one ball of, say that there's a black ball and then there's a green ball, so if we happen to pick up a black ball now, we put one black ball into this box, that means that the capacity now goes down from 100 to 99. Do we get? And now we sort of like have a different problem now. The new problem is, how do we now what's the best way to fill up a bag with a capacity of 99 using these balls? So you see, that could have been one option. The other option it could be is, so one option is to say we take a ball of capacity 1. The other option is we take a ball of capacity 50. The other option is we take a ball of capacity X. The other option we take a ball of capacity Y. Yeah, so at every point when we do that, the capacity of the bag now goes down. So the capacity of the bag here now is 99, the capacity of the bag here now is 50. Capacity of the bag here now will be 100 minus x, and capacity of the bag here will be 100 minus y. And then at this point now we have the same set of options. Yeah, remember it's unbounded. So we can either take the bag capacity 1, capacity of 50, capacity of x, capacity of y, if we have other options. So when we do this, we now have a bag capacity of 98. Here we would have a bag of capacity of 49. Then here we'll have a bag of capacity of 99 minus x, 99 minus y. So we keep doing this and doing this until it no longer makes sense to take a capacity. So say for example now, at this point we want to take a bag, we can choose to take capacity 1, capacity 50, capacity x, capacity y. But if we attempt to take a capacity of 50, we see that we surpass the capacity of the bag. So this is an invalid option. So that is the way we identify the options that are invalid. Yeah, does that make sense? Yeah, so basically what we do is within the function, we would loop through all the options, take up an option, keep the value of that option, and then recursively call the same function with a reduced size of the capacity. So if that makes any sense, so that now means that we would have a DP function that takes in the capacity of the bag. And that's all. That's all we need. So with the capacity of the bag, within this loop, we will now go through all of the, all of the elements within all of the weights that we've been given, combination of the weights and the watts of those bags. What's it called again? Called values, and then for each one of them we call, so for every one that we take, we call dp of the capacity minus the weight. And when we call this, so for each, let's say for each of the n, so we'll say like that particular n, and then we have that value, say that v is the value, so we have that value as as the result from here. So this now becomes a different problem, a sub problem, and then we recursively call this function over and over. And when we do this for all of the options, and as we do this for all of the options, we could have like a value here that will represent the maximum we can get. The maximum it could be maybe 0, it starts from 0, and then we'll now say, okay, this is the value that we've computed from adding these two together, from this particular, say here for the part of 1, this is the value we've computed. At the end of the day, we'll now say, okay, so the maximum will now be the maximum of that max, we will update our max to the maximum of that max and this new value that we computed. And then once we are done, yeah, I mean, this is the solution to this problem. And remember, we always need to have a base case. In this time around, the base case will be, remember this point, the base case is when we can no longer go down. Yeah, so at this point here, we can always check. Yeah, so if the capacity, if the capacity is less than the size of this weight, then we don't check, we don't go down recursively. So we have our base case here. Although there's another way we could do it. We could have a situation where we put our base case, like the way we've always done it. So we will say that if the capacity is -1, for example, or rather the capacity is less than 0, we just return -1. And then when we have this DP calculation, we need to now check if this is -1, we know that this is an invalid part, so we don't use this one. Yeah, so this is basically what it looks like. And then if we have to analyze the time complexity of this, we'll know that we are technically, so for every capacity that we have, we end up splitting it into how many options. You see the options that we have. So the options we have is 1, 2, 3. Basically, the options we have are all the options for so we could split into, this is one option. Remember, this is a for loop. The for loop will run the number of elements we have inside this weight. Yeah, so if we say that the number of inputs we have inside the weight is W, so that is W that is W, then raised to power the size of this capacity. Yeah, and then another way you could do it, you could actually, it's not entirely raised to the power size of this capacity, but it is. Yeah, so we could also say that if we really want to go fine grain, we could say that the minimum size of the element within this capacity, divided by, so let's say the minimum of the elements within this width. Yeah, because that determines how many times we're going to call this function. Remember, how many times we call this function is what is up here. And then, so this is like roughly around what it looks like. This is exponential. This is bad. Exponential, remember, in relation to the inputs, the capacity. But we could do better than this, yeah, if we memorize. So that's all we have to do. So once we memorize this, so the same thing, we have a memo. And then this time around, when we are memorizing, we're memorizing using the capacity. Remember, we memorize, the key is always the value that is changing inside the parameter that is being passed, which is the capacity. So we evaluate for a particular capacity, and then we know that if we come across the capacity again, we don't longer need to evaluate for it anymore. We just return it. So we have like an if check here to check if that value is already in the memo. If it is, we return it back. Otherwise, yeah, we memorize. We put into that memo these marks for the capacity. So we say at the capacity position, we put marks. Alright, so remarkably, this reduces this problem from this complexity it has into one whereby we only evaluate every one of this capacity once. So at the end of the day, we now have a O of C capacity. Yes, O of C. However, because within each of these capacity, we loop through all the different options we have in the weights, it now becomes O of C times W. Remember when I said that we'll have a situation where dynamic programming reduces a problem from an exponential time solution into a polynomial time solution. So this is an example. Yeah, so this is polynomial time compared to an exponential time solution. All right, so regarding space complexity is basically just the same, the depth that you can go, which is going to be this C over minimum. Yeah, so that's basically like, let's say, C over minimum of the width, and is actually, think about it, is most likely the same for both parts because the depth of the tree we can go is either of this. All right, so this is basically how this problem is solved. And I remember I said that recursive approach is usually the easiest way to think about it. And then this is the recursive way to solve this problem. All right, guys. So thank you once again for joining me in another session. See you guys in another dynamic programming pattern video where we'll talk about the next pattern on this list, which is the Cardinals algorithms pattern. Please don't forget to like, share, and subscribe. See you guys in another video. Bye.